Have you ever stopped to think about what's actually going on inside your phone when you're juggling a bunch of apps? It's easy to picture the processor as this single brilliant soloist doing everything, but the reality? It's way more like a huge, complex orchestra. And that's a really cool solution, but it kind of makes you wonder, why didn't we just build one giant, super fast brain to start with? And that's a perfectly fair question, because for decades, that was the entire game plan. The strategy was simple. Just make that one soloist faster, and faster, and faster. But eventually, we slammed right into a physical wall. I mean, literally, the laws of physics and the sheer amount of heat we were generating made it impossible to keep pushing that single-core speed. So, the whole industry had to completely change its tune. And that really was the end of the solo performance. The solution wasn't about making the one musician play faster anymore. Nope, it was time to bring in more musicians. The new strategy was all about teamwork, dividing the work among a whole team of processors, all playing in harmony. So this big shift towards teamwork led to two main strategies for splitting up all that computational work. The first one is kind of like having a team of really good all-arounders, and the second is more like calling in the absolute top-tier specialists. Let's break down what that actually means. So first up, let's talk about multiprocessing. Just stick with that orchestra analogy for a second. Think of this as your team of generalist musicians. They can all read the main sheet music, they can all play the melody, and because they're working together, they can get the whole piece done way, way faster than any single one of them could on their own. So the official definition is using multiple general-purpose CPUs, what we all call cores these days, to work on tasks at the same time in parallel. This is the magic behind how your computer can run a web browser, a video call, and a bunch of spreadsheets all at once without just stopping. It's a huge boost to the total amount of work the system can get through. Okay, but once you have a team, you've got a new problem, right? You need to manage them. You can't just have an orchestra where every musician decides to play whatever they feel like. You need a conductor, or at the very least, you need everyone to be on the same page. And in the world of multiprocessing, two main management styles popped up. And what's really fascinating here is how it boils down to two very different philosophies. On one side, you have Symmetric Multiprocessing, or SMP. This is your democracy. All the processors are equals, they're peers. They all have the same access to everything, and any of them can run any task. It's super flexible, and it scales up beautifully. Then, on the other side, you've got Asymmetric Multiprocessing, or AMP. This is more of a top-down master-slave model. You have one master processor handling all the important stuff and just handing out tasks to the slave processors. Now, it's simpler to set up, but you can probably spot the problem already. That master can get overwhelmed and become a serious bottleneck. This diagram just makes that difference crystal clear. See, on the left with the symmetric model, all the CPUs are just grabbing tasks from a shared to-do list. It's a real team effort. But over on the right, the asymmetric model has a clear chain of command. The master is the only one dealing with the main system, and it tells the slaves what to do. It's probably no surprise that pretty much all modern systems use the symmetric model because it's just so much more efficient. And what's really mind-blowing is that this whole idea doesn't just stop inside your laptop. It's the exact same principle that powers the gigantic server farms and cloud computing clusters that basically run the internet. But here, instead of tiny cores on a chip, you have whole computers linked up by a network, all working in parallel. It is multiprocessing on an absolutely massive scale. Okay, so your generalist musicians are great, but what happens when you have tasks that are just way too specific or crazy demanding for them? Well, that's when you call in the specialists. And this brings us to our second big strategy, coprocessing. This is your orchestra's first-chair violinist or that percussionist who is a total virtuoso. Right, the whole point of a coprocessor is that it's a special chip designed to do one particular job and do it incredibly well. It offloads really specific work. We're talking heavy-duty math, rendering graphics, processing audio. It takes that off the main CPU's plate. This frees up that generalist CPU to focus on running the operating system and your apps, and it just makes the entire system faster and a whole lot more efficient. And this idea isn't new at all. It's just gotten more advanced. Back in the 80s, you had the Intel 8087, which is basically a dedicated math coprocessor. It was a total game changer for things like spreadsheets. Then, of course, came the GPU, the ultimate specialist for graphics. And today, the smartphone in your pocket has motion coprocessors that track your steps and know which way you're holding the phone, all while using a tiny, tiny amount of power, something the main CPU would be terrible at. So if we take these two big ideas, the team of generalists and the squad of specialists, and we bring them together, what we get is basically the blueprint for every single modern computing device out there. We get the full digital orchestra.
Now, there is a fancy technical term for this. It's called heterogeneous computing. It's really just a way of saying we use a mix of different types of processors, where each one is perfect for a different kind of task, and they all work together in harmony. You get the best of both worlds. And here's a little peek under the hood. This diagram gives you the basic structure. You've got your multiple processing units, could be generalist CPUs, could be specialist coprocessors, and they're all hooked into the main memory and the input/output systems. This shared connection, this plumbing, is what lets them all collaborate and work together on the same set of tasks. To make this super real, just think about your smartphone. It is a perfect example of a modern digital orchestra. You've got your multi-core CPUs as a generalists. You've got a GPU, the graphics specialist, making your screen look beautiful. You've got an AI accelerator for things like Siri or Google Assistant. You've got a digital signal processor for audio and that motion coprocessor for all the sensors. Every single one is a master of its own craft. So we've come all this way, from a single soloist to this full-blown digital orchestra. What does that journey tell us about where computing is actually going? Well, the biggest takeaway is really summed up right here. Modern computer performance isn't about having one hero chip that's the fastest. Not anymore. It is all about how well the hardware and the software can make a diverse team of different processors play together in perfect harmony. And that leaves us with a really fascinating question for the future, right? As the things we do with our computers, from AI to virtual reality, get more and more specialized, are we going to see that balance shift? Is it possible that the digital orchestra of tomorrow will be made up almost entirely of specialists, with maybe just a few generalists left to conduct them? It's definitely something to think about. Well, I really hope this peek inside the computer's orchestra helped clear up just how our devices manage to do so much so fast. And if you enjoyed this explainer, do us a favor and help other people find it by hitting that like button. And of course, be sure to share it and subscribe to Tech Talk 101 for a lot more deep dives into the tech that shapes our world. Thanks for tuning in. We'll see you in the next one.